Our preconceived notions are being challenged by the James Webb Telescope. Numerous galaxies that are far too big and massive for their early development have already been discovered by it. This brings up an important question. May we have miscalculated the universe's origin if we had previously made mistakes in our models of early galaxy evolution? Despite being widely accepted for a long time, the Big Bang theory is today facing more and more criticism. Therefore, it is plausible that everything did not begin with the Big Bang. After all, it was only one of an endless number of changes, and by no means the cosmic starting signal. Given this, the next fascinating query is not far off. What was there before the Big Bang? Before expansion began around 14 billion years ago, the entire universe was hot and dense. The Big Bang Theory's cult nerd sitcom viewers are not the only ones who understand how the universe came into being. As we currently understand it, the frequently mentioned Big Bang explains how space, time, and matter formed from an initial singularity some 13.8 billion years ago, opening the door for everything that exists today and will exist in the future. Thus far, so kindly presumed. However, how can we possibly know what occurred 13.8 billion years ago? The answer is rather straightforward, by taking a backward look at a development that started with the Big Bang and is still going strong now. As is widely known, the universe is a construct that has been continuously expanding from the beginning of time rather than a hard, unchanging object. It should be noted at this point, for the sake of clarity, that the universe is not expanding into an already existing space, but rather that space itself is expanding continuously. With the aid of Einstein's general theory of relativity, we can now follow the universe's expansion back in time until we reach a point where all spatial distances are zero and the density of matter and energy is limitless. We have so returned to the hot, dense state described in the introduction of the Big Bang theory. But there are other factors outside theoretical calculations that have contributed to the Big Bang theory's current prominence. Indeed, the cosmic background radiation is another factor. This microwave radiation, which was produced some 380,000 years after the universe's creation, is still present across the cosmos today. The actual observation of the aforementioned radiation is regarded as crucial evidence for the Big Bang theory since it was theoretically expected in the Standard Model. However, we must remember that the Big Bang still leaves more questions than it answers, even with all the mathematical models and discovered radiation relics. According to our understanding, the original cosmos must have expanded by a factor of 1,030 to 10,100 in this absurdly small time span, and it must have undergone the first significant growth spurt in fractions of a second. The question of whether cosmic inflation actually happened and how it happened is as ambiguous as the question of whether anything existed before to the Big Bang. In actuality, not all cosmic mysteries can be resolved by the Big Bang theory alone. The topic of what truly transpired during the cosmic birth's background is one example. To put it another way, what caused anything to appear out of thin air 13.8 billion years ago? Was it purely coincidental, or was there a trigger? And how is it possible for matter to form from nothing? Well, Stephen Hawking took a straightforward and sensible approach to this difficult subject. The question of what was before the Big Bang is just as pointless as asking which is north of the North Pole, because time itself only began with the Big Bang. The brilliant person, who passed away in 2018, was quoted as saying, "There is nothing or no one that could have caused this incident. The universe might have formed without energy or a cause, according to the rules of nature themselves." But more on that in a bit. Other scholars, however, have issues with this premise specifically. The topic of why matter and radiation are so uniformly distributed in the universe is equally contentious. On a broad scale, radiation, gas nebulae, and galaxies all exhibit comparable densities and distributions, regardless of the direction or distance we gaze. Though some scientists argue that this process is still ongoing today and that many parallel universes have emerged in the process, the current theories lead to cosmic inflation at this time. The theory of Big Bounce. Despite its widespread acceptance, the Big Bang is far from being uncontroversial, and its origins remain mostly unknown. This is a minor intermediate conclusion. Alternative theories that attempt to provide a whole new explanation for the cosmic genesis question have surfaced over time. We must give up the notion that the Big Bang was the origin of everything, notwithstanding the fact that the related theories occasionally diverge significantly from one another. The Big Bang would be better characterized as the Big Bounce if there had been a previous universe, since it was only the explosive transition from one universe to the next. However, what does that actually mean? Does the existence of such a cyclical universe have any concrete evidence? The concept of the interaction between rebirth and destruction is not new, at least not in theory. For instance, the universe is described in the early Indian Vedas as a perpetual cycle of creation, destruction, and restoration. The worldview of the Maya was quite close to Einstein's, who considered that the concept of an oscillating, cyclical universe was perfectly realistic, in keeping with the maxim, what expands can also contract again. In cosmology, cyclic models are still widely used today. It should come as no surprise that this method can avoid the issue of cause. If matter has always been in a perpetual cycle, then the question of how something can come into being out of nothing is equally moot. There simply has never been an absolute nothing in such a situation. In this instance, cosmic contraction, which distributes almost everything equally, could also account for the universe's odd homogeneity. It would be equally simple to identify the trigger for the Big Bang, the conclusion of the preceding cycle, followed by a new expansionary phase. Therefore, if it weren't for the entropy problem, things might be so straightforward. The second law of thermodynamics states that a closed system's degree of disorder always rises, and the cosmos is no exception. Therefore, entropy would have to build indefinitely due to the constantly occurring cycles. Accordingly, the universe will eventually reach a maximum entropy condition where atoms, stars, and galaxies cannot exist, and with every cosmic new beginning, a bit more radiation is produced in relation to matter. That's not all, though. With each contraction of the cosmos, the entropy problem would cause an increasing number of disordered particles to be crushed together, while a stronger dispersal would accompany the next fresh beginning. On the other hand, this just implies that every new cycle would always be a bit longer than the one before it. However, this would also imply that the farther back we look, the shorter the cycles are in comparison to the past. We would also reach a starting point where everything is concentrated, the forgetfulness of the universe, much like with the Big Bang idea. Quantum gravity loop. Can we put the cycle models away now? After all, a primitive origin for everything is expressly rejected by the comparable theories. Well, we shouldn't be so hasty to rule out the possibility of an unending cycle. The entropy problem can actually be solved by scientists now. All it needs is a universe that is experiencing a severe case of memory loss. We must briefly stray into the realm of loop quantum gravity in order to comprehend what this means. In contrast to Einstein's presumptions, this theory holds that spacetime is not continuous, but rather is made up of small, indivisible components. The Planck length, the lowest unit of quantum theory, is equivalent to the extent of these autonomous loops, which range from 1035 meters. The particles are the nodes of the net-like structure, which is made up of interwoven loops that together constitute the fundamental structure of the universe. In this sense, we might think of the universe as a single web of ever-evolving, minute connections that are invisible to the naked eye. The universe's first singularity could not have existed in this setting. An infinite density is not possible in loop quantum gravity since it only permits finite physical values. However, in the same sentence, the quantization results in an equally stunning event. Gravity is reversed at the Big Bang point. Suddenly, instead of its typical seductive force, it pushes everything away. Space is essentially turned inside out as a result, which has some startling repercussions. As a result, the loop model blatantly asserts that everything did not begin with the Big Bang. It also produces sound mathematical results before to the Big Bang, which is different from the theory of relativity. In the event that a predecessor universe collapses in on itself and is subsequently forced back onto bigger scales by the anti-gravitational impact of its own tiny network, this phenomenon is known as a Big Bounce. All knowledge from the earlier universe would be conveniently erased by the ensuing changes in matter and energy density. Put another way, every new world experiences a severe case of memory loss, which, since it is essentially reset to zero, also solves the entropy problem. The universe can start over without worrying about its previous entropy burdens. You can now join our community. Hit the like and subscribe buttons and never miss another one of our videos. See you soon.